Ah, the expanding universe. You know, when I sit here in the quiet of the evening, gazing up at the stars, I cannot help but marvel at what we have discovered about the cosmos. It is, it is perhaps the most profound realization of the 20th century that everything we see, everything we know, all the galaxies scattered like luminous pearls across the dark fabric of space, they are all rushing away from one another like raisins in a rising loaf of bread. You see, you see, for the longest time, thousands upon thousands of years, humanity looked up at the night sky and saw permanence. The ancient Greeks called them the fixed stars, yes? They believed the cosmos was eternal, unchanging, a crystalline sphere, perhaps, rotating around our Earth. Even when we learned that Earth was not the center, even when Copernicus and Galileo showed us our true place, still, we thought the universe itself was static, eternal, unchanging in its grand architecture. But then but then came the 1920s, and with it, a young astronomer named Edwin Hubble. Now, Hubble was working at the Mount Wilson Observatory in California using what was then the most powerful telescope in the world, a 100-inch reflector. And what he discovered, well, it changed everything. He was studying those fuzzy patches of light we call nebulae, and he noticed something peculiar, something that at first seemed almost impossible. The light from these distant galaxies, for that is what they were, entire galaxies like our own Milky Way, the light was shifted toward the red end of the spectrum. Now, this red shift, as we call it, it's like um, imagine you are standing by a railway track and a train approaches you blowing its whistle. As it comes closer, the sound is higher in pitch, yes? And as it moves away, the pitch drops lower and lower. This is the Doppler effect, and light behaves in a similar way. When something moves away from us at tremendous speeds, its light stretches out, becomes redder. But here's the remarkable thing, and this is what made Hubble's discovery so revolutionary. Almost every galaxy he observed showed this redshift, and not just a little bit. The farther away the galaxy, the greater the redshift. It was as if the entire universe was expanding, stretching like a balloon being inflated, carrying all the galaxies away from each other. Now, I must confess something to you. When I first developed the equations of general relativity in 1915, they predicted exactly this, an expanding or contracting universe. But I couldn't believe it. It seemed so contrary to everything we thought we knew. So I introduced what I called the cosmological constant, a kind of a fudge factor, you might say, to keep the universe static in my equations. Later, I would call this the greatest blunder of my life. You see, sometimes even in science, our preconceptions can blind us to the truth that our own mathematics is trying to tell us. The implications of Hubble's discovery were, well, they were staggering. If the universe is expanding now, then if we run the clock backward, everything must have been closer together in the past. Go back far enough, and everything, all the matter, all the energy, all of space itself must have been compressed into a single point. This is what we now call the Big Bang, though I must say the name is somewhat misleading. It wasn't an explosion in space, it was an expansion of space itself. Think of it this way. Imagine you have a deflated balloon, and on its surface you've drawn little dots to represent galaxies. As you inflate the balloon, every dot moves away from every other dot. No dot is at the center, or rather, every dot can consider itself the center, because from its perspective, everything else is moving away. This is, this is how our universe works. We are not at the center of the expansion. There is no center. Every point in space is expanding away from every other point. The rate of this expansion, we call it the Hubble constant. though as we've discovered, it's not quite so constant after all. Currently, we measure it at about 70 kilometers per second per megaparsec. What does this mean in simple terms? Well, for every megaparsec, that's about 3.26 million light years, that you look out into space, galaxies are receding from us an additional 70 kilometers per second faster. But here's where it gets even more interesting. In 1998, two teams of astronomers were studying distant supernovae. These are exploding stars that serve as what we call standard candles because we know how bright they should be. And what they found, it shocked everyone. The expansion of the universe is not slowing down as we would expect if gravity were the only force at work. No, the expansion is accelerating. Imagine Imagine throwing a ball up into the air, and instead of it slowing down and falling back, it speeds up as it rises, flying away faster and faster. This is what our universe is doing. Something, we call it dark energy, though that's really just a name for our ignorance, something is pushing space apart with ever increasing vigor. This dark energy, it comprises about 68% of the total energy density of the universe. Dark matter, that mysterious substance that doesn't emit light but whose gravity holds galaxies together, makes up another 27%. And ordinary matter, the atoms that make up you and me, the stars, the planets, everything we can see, we are less than 5% of the universe. We are we are like children who have found a few grains of sand on a vast beach and think we understand the ocean. The geometry of this expanding universe. Ah, this is something that fascinated me greatly in my work on general relativity. Space itself can be curved, you see. On large scales, the universe could be positively curved like a sphere, negatively curved like a saddle, or flat like an infinite plane. Current measurements from the cosmic microwave background, the afterglow of the Big Bang itself, suggest that our universe is remarkably flat, at least within the limits of our measurements. But flatness raises its own mysteries. Why should the universe be so perfectly balanced between being positively and negatively curved? It's like balancing a pencil on its point. The slightest deviation in the early universe should have led to a dramatically different geometry today. This is what we call the flatness problem, one of several puzzles that led to the theory of cosmic inflation. Inflation. Now, this is a remarkable idea. In the first tiny fraction of a second after the Big Bang, we're talking about 10 to the minus 35 seconds, the universe underwent a period of exponentially rapid expansion. In less time than it takes light to cross a proton, the universe expanded by a factor of at least 10 to the 26. It's it's almost incomprehensible, really. This inflation would explain not just the flatness, but also why the universe looks so uniform on large scales, why the cosmic microwave background temperature is so remarkably constant across the sky. You know, as I sit here contemplating these vast scales and enormous energies, I'm reminded of something. The universe is not just expanding in space, but also in time. We are living in a particular moment in cosmic history. Billions of years ago, the universe was denser, hotter, more violent. Billions of years from now, if the acceleration continues, galaxies will be so far apart that future astronomers, looking up at their night sky, might see only their own galaxy, alone in an empty void, the loneliness of that future universe. It haunts me sometimes, you know. Here we are, in what you might call the golden age of astronomy, when we can still see the cosmic web stretching across billions of light years, when we can still detect the faint whispers of the Big Bang in the microwave background. Future civilizations, perhaps 100 billion years from now, will look out and see darkness. The accelerating expansion will have carried all other galaxies beyond what we call the cosmic horizon. This cosmic horizon, it's a peculiar concept, really. You see, because light travels at a finite speed, and because the universe has a finite age, about 13.8 billion years, there is a limit to how far we can see. We call this the observable universe. It's like being in the middle of the ocean on a foggy day. There's more ocean beyond what you can see, but the fog, or in our case, the finite speed of light and the age of the universe, prevents us from seeing it. But it gets even more interesting. Because space itself is expanding, there are regions of the universe that we will never ever be able to see, no matter how long we wait. The light from these regions is trying to reach us, but space is expanding faster than the light can travel through it. It's like trying to walk up an escalator that's moving down faster than you can climb. These regions are beyond our event horizon, causally disconnected from us forever. Georges Lemaitre, the Belgian priest and physicist who first proposed what we now call the Big Bang theory, he called it the primeval atom or the cosmic egg. He understood something profound about this expansion. He realized that if we truly understand the expansion, we must also grapple with the question of beginnings. What caused the expansion? What was before the Big Bang? These are questions that push us to the very limits of what science can address. Now, before we continue deeper into these mysteries, I'd like to ask you to subscribe to the channel to help me reach the first 1,000 subscribers here. The purpose of this channel is to help you fall asleep with high-quality knowledge, right? It doesn't cost anything. Just hit that subscribe button. You know, I've been thinking about the different models cosmologists have proposed for this expansion. The steady-state theory, championed by Fred Hoyle and others in the mid-20th century, suggested that as the universe expands, new matter is continuously created to fill the gaps, keeping the overall density constant. It was an elegant idea, really, a universe without beginning or end, eternal and unchanging on the large scale despite the expansion. But the discovery of the cosmic microwave background in 1964 by Arno Penzias and Robert Wilson, well, that was the death knell for steady state. The universe clearly had a hot, dense beginning. Then there's the cyclic model, the idea that our universe goes through endless cycles of expansion and contraction. Big Bang, expansion, eventual contraction into a big crunch, then another Big Bang, over and over like a cosmic heartbeat. It's a romantic notion, isn't it? A universe that never truly dies but is reborn again and again. But the discovery of accelerating expansion makes this seem unlikely, unless dark energy changes its nature over time. And this is where things get truly mysterious. Dark energy, we've given it a name, but we don't really know what it is. Is it a property of space itself, what we call vacuum energy? You see, even completely empty space, according to quantum mechanics, is not truly empty. It seethes with virtual particles popping in and out of existence, creating a kind of energy density. But when we calculate how much vacuum energy there should be, we get a number that's, well, it's 120 orders of magnitude larger than what we observe. This is perhaps the worst prediction in the history of physics. We call it the cosmological constant problem, or perhaps dark energy is something else entirely, a new kind of field that fills all of space, what we call quintessence. Unlike the cosmological constant, which remains constant, quintessence could change over time. It could even theoretically change its nature from repulsive to attractive, though we've seen no evidence of this. Robert Dickey and Jim Peebles at Princeton, they've done remarkable work on the large-scale structure of the universe. They've shown us that the expansion isn't perfectly smooth. There are variations, tiny fluctuations in density that were present even in the early universe. These fluctuations, amplified by gravity over billions of years, became the seeds of all the structure we see today. Galaxies, clusters of galaxies, the vast cosmic web of filaments and voids. The Sloan Digital Sky Survey, mapping millions of galaxies, has shown us this structure in unprecedented detail. It's It's breathtaking, really. Galaxies aren't scattered randomly through space. They form vast walls and filaments with enormous voids between them like soap bubbles on cosmic scales. And all of this structure is being stretched apart by the expansion, growing ever larger, ever more diffuse. Temperature plays a fascinating role in this story too. As the universe expands, it cools. Right now, the average temperature of the cosmic microwave background is about 2.7 Kelvin, just barely above absolute zero. But in the early universe, it was billions of degrees. The expansion of space literally stretched the wavelengths of light, cooling the universe from a blazing inferno to the cold, dark cosmos we see today. Saul Perlmutter, Adam Rees, Brian Schmidt. These are the astronomers who led the teams that discovered the accelerating expansion. They were studying type Ia supernovae, using them as standard candles to measure distances in the universe. What they expected to find was that the expansion was slowing down, that gravity was gradually pulling things back together. What they found instead, it changed everything we thought we knew about the cosmos. I think about the James Webb Space Telescope, now peering deeper into space and further back in time than ever before. It's showing us galaxies as they were when the universe was just a few 100 million years old, when the first stars were igniting in the darkness. These observations are helping us understand how structure formed in the expanding universe, how the first galaxies assembled from the primordial gas. The expansion also affects time itself, you know. This is something that follows from relativity. Time and space are interwoven into space-time, and as space expands, time is affected too. The photons from distant galaxies are not just redshifted, they're also time-dilated. We see distant supernovae exploding in slow motion, their light curves stretched by the expansion of space. You know, there's something I find deeply peculiar about this whole business of expansion. Gravity, the force that pulled together the atoms to form stars, that holds you to the earth right now as you listen to these words. Gravity always attracts, never repels. Yet here we have the universe doing exactly the opposite of what gravity should make it do. It makes one wonder if we truly understand gravity at all. General relativity tells us that mass and energy curve space-time, and this curvature is what we experience as gravity. But on the largest scales, something else is at work. The equations, the equations allow for it, yes, but understanding what it means, that's another matter entirely. It's as if the universe has two opposing tendencies built into its very fabric, the tendency to pull together through gravity and the tendency to fly apart through this mysterious dark energy. Now, here's a thought that keeps me awake sometimes. What about the spaces between spaces? I mean, we say space is expanding, but expanding into what? This is this is where language fails us, really. Space isn't expanding into anything. It's not like a balloon expanding into the room around it. Space itself is all there is, and it's creating more of itself. New space is appearing between galaxies, between stars, even between atoms, though the effect is far too small to measure at such scales. Alan Guth at MIT, when he proposed inflation theory in 1980, he realized something profound. The energy that drives inflation, it doesn't dilute as space expands, not like ordinary matter or radiation. It's it's like a peculiar kind of substance where, as you create more space, you create more of the energy that creates space. It's almost like a chain reaction, but in the fabric of reality itself. This is why inflation, once started, tends to continue eternally in most models. Speaking of eternal inflation, this is where things get truly mind-bending. Andre Linde at Stanford has shown that in many inflation models, inflation never completely stops everywhere. It ends in some regions, these become universes like ours, but continues forever in others. The result is what we call the multiverse. an infinite fractal of pocket universes, each potentially with different physical laws, different constants of nature. Some of these pocket universes might expand forever, like ours appears destined to do. Others might collapse. Some might have no stars, no complexity, just empty space or a soup of particles. We might be living in the only kind of universe where beings like us can exist to contemplate these questions. This is this is what we call the anthropic principle. Though I must confess, it makes me somewhat uncomfortable. It seems to give up on finding a deeper explanation for why things are the way they are. The particle horizon is another fascinating consequence of expansion. Because the universe has a finite age and light travels at finite speed, there's a maximum distance from which light has had time to reach us since the Big Bang. This horizon grows with time, of course. Every second, light from slightly more distant regions reaches us for the first time. But because of acceleration, there's a limit to how much we'll ever be able to see. The observable universe will reach a maximum size and then, in a sense, begin to shrink as galaxies pass beyond the cosmic event horizon. Leonard Susskind and his work on the holographic principle, it suggests something remarkable about space itself. The maximum amount of information that can be contained in a region of space is proportional not to its volume, but to the area of its boundary. It's as if all the information about what's inside a region is somehow encoded on its surface. What does this mean for an expanding universe? As space expands, is new information being created? Or is existing information being diluted somehow? The LCDM model, lambda cold dark matter. This is our current standard model of cosmology. Lambda represents dark energy, the driver of acceleration. CDM is the cold dark matter that provides the gravitational scaffolding for galaxy formation. Together with ordinary matter, radiation, and the initial fluctuations from inflation, this model explains virtually everything we observe about the large-scale universe, and yet it's built on two complete mysteries, dark matter and dark energy, that together make up 95% of the universe. When I think about the cosmic web, those vast filaments of galaxies with voids between them, I'm reminded of neurons in a brain, or the mycorrhizal networks that connect trees in a forest. The universe has structure on every scale, from subatomic to cosmic, and this structure is dynamic, evolving, shaped by the interplay of expansion and gravity, the Hubble tension. Now, this is a puzzle that's emerged in recent years. When we measure the expansion rate using the cosmic microwave background and the physics of the early universe, we get one value. When we measure it directly using supernovae and other distance indicators in the nearby universe, we get a different value, about 9% higher. This discrepancy, it might be telling us something profound. Perhaps dark energy is not constant after all. Perhaps there's new physics we haven't discovered yet. Wendy Friedman at the University of Chicago, she's been using a different approach, red giant stars as distance indicators, trying to resolve this tension. The results are, well, they're somewhere in between the two conflicting measurements. The universe, it seems, is not ready to give up its secrets easily. I sometimes imagine what it would be like to watch the expansion over cosmic timescales. In the early universe, just minutes after the Big Bang, the expansion rate was tremendous. The universe doubled in size in just seconds. Now it takes about 10 billion years for the universe to double in size. But as dark energy becomes more dominant, this doubling time will decrease again. The thermodynamics of expansion. This is something that troubled me for many years. As the universe expands and cools, entropy increases as the second law of thermodynamics demands. But gravity complicates things. A uniform gas has high entropy, but in a universe with gravity, the highest entropy state is black holes. And in an eternally expanding universe, even black holes eventually evaporate through Hawking radiation, leaving behind what? An empty space filled only with sparse radiation, maximum entropy, what we call the heat death of the universe, the Cepheid variables. You know, Henrietta Swan Leavitt discovered their remarkable property in 1908, working at Harvard Observatory. She was studying photographic plates, thousands upon thousands of stars, when she noticed that these pulsating stars had a peculiar relationship. The brighter they were, the longer their period of pulsation. This period luminosity relationship became our first reliable cosmic yardstick, our way of measuring distances far beyond what parallax could reach. It was actually Cepheids that Hubble used to prove that those spiral nebulae were actually other galaxies, far beyond our Milky Way, and it was Cepheids that first revealed the expansion. But in an expanding universe, even distance becomes a slippery concept. What do we mean by the distance to a galaxy? The distance when the light left it, the distance now, the distance the light traveled? These are all different in an expanding cosmos. The co-moving distance. This is how cosmologists handle this complexity. We imagine a coordinate system that expands with the universe like a grid painted on that inflating balloon I mentioned earlier. In these coordinates, galaxies stay roughly fixed. It's the space between them that grows. It's a mathematical convenience, but it helps us make sense of observations. Roger Penrose, with his conformal cyclic cosmology, he proposes something radical. He suggests that the far future of our expanding universe, when all matter has decayed and only photons remain, is mathematically identical to the Big Bang of a new universe. The end becomes the beginning, but not through a big crunch, through a kind of mathematical sleight of hand where infinite future time becomes zero time in a new cosmic epoch. It's beautiful mathematics, though whether it describes reality, that's another question. You see, the expansion affects everything, even atomic processes, though the effect is utterly negligible. The electromagnetic force that holds atoms together is so much stronger than the expansion that atoms don't grow. Neither do solar systems or galaxies. Gravity overwhelms the expansion on these scales. It's only in the vast voids between galaxy clusters that expansion truly dominates. It's like a gentle tide that only moves things that aren't anchored down. The Atacama Cosmology Telescope in Chile, the South Pole Telescope in Antarctica. These instruments are mapping the cosmic microwave background with exquisite precision, looking for the tiniest variations, the fossil imprints of those quantum fluctuations that inflation stretched to cosmic scales. Every new measurement constrains our models further, tells us more about how the expansion proceeded in those first crucial moments. I find myself wondering about consciousness in an expanding universe. If the universe continues to accelerate, if the Big Rip scenario comes to pass, where eventually even atoms are torn apart by expansion, what happens to information, to memory, to thought itself? These are questions at the boundary between physics and philosophy. The red shift we observe, it's not really a Doppler shift, not in the traditional sense. The galaxies aren't moving through space away from us. Rather, space itself is stretching, and the light waves stretch with it. It's a fundamentally different phenomenon, though the mathematics look similar. This cosmological redshift is a signature of the expansion itself, written in the light of distant stars. Fritz Zwicky, that irascible genius, he coined the term dark matter in the 1930s, but he also proposed tired light as an alternative to expansion. Perhaps, he suggested, light simply loses energy as it travels vast distances, becoming redder without any expansion at all. But tired light can't explain all our observations. The time dilation of distant supernova, the spectrum of the cosmic microwave background, the expansion is real. WMAP, the Wilkinson microwave anisotropy probe, and later Planck, the European Space Agency's mission. These satellites have given us baby pictures of the universe, maps of those tiny temperature variations in the cosmic microwave background when the universe was only 380,000 years old. The patterns in these maps, they're like fingerprints of the expansion, telling us about inflation, about the curvature of space, about the contents of the universe. The BAO, baryon acoustic oscillations, these are frozen sound waves from the early universe. Before atoms formed, the universe was filled with a hot plasma where sound waves could propagate. When atoms formed and the universe became transparent, these sound waves froze, leaving a characteristic scale imprinted on the distribution of galaxies. As the universe expands, this scale expands too, giving us another way to track the expansion history. You know what fascinates me? The expansion means that most of the universe is already forever beyond our reach. Even if we could travel at the speed of light, we could only ever reach galaxies within about 15 billion light years. Everything else is being carried away by expansion faster than we could ever travel. We are like islanders on a shrinking island, though it's not the island that shrinks, but the ocean that grows. The integrated Sachs-Wolf effect. This is a subtle phenomenon where cosmic microwave background photons gain or lose energy as they pass through the gravitational wells of galaxy clusters in an expanding universe. In a static universe, the energy gained falling in would exactly cancel the energy lost climbing out. But expansion changes the depth of these wells while the photon is traversing them. It's like surfing on waves that are themselves changing as you ride them. Void galaxy surveys are showing us the emptiest regions of space, vast bubbles hundreds of millions of light years across with almost no galaxies. These voids are expanding faster than the denser regions, as they have less gravity to resist the expansion. They're like windows into what the far future universe will look like when expansion has diluted everything to near nothingness. The Erecita telescope, launched in 2019, is conducting an all-sky survey in X-rays, mapping the hot gas in galaxy clusters. This gas traces the gravitational scaffolding of the universe, showing us how expansion and gravity compete on the largest scales. Each cluster is like a laboratory where we can study this cosmic tug of war. Something that puzzles me deeply. If space can expand, can it also contract locally? Not just from gravity, but from some other mechanism? Could there be regions where space itself is destroyed, just as it's created in expansion? These are the kinds of questions that keep theoretical physicists awake at night, wondering about the fundamental nature of space-time itself. Mass tells space-time how to curve, and space-time tells mass how to move. This was my geometric vision of gravity. But in an expanding universe, space-time does something else entirely. It grows. And this growth, this expansion, it happens even in the absence of any mass or energy to push it. Empty space itself has a tendency to expand, as if the vacuum has a kind of pressure, a tension that drives it ever outward. The neutrinos, these ghostly particles that barely interact with matter, they're fossils from when the universe was just 1 second old. There should be about 300 of them in every cubic centimeter of space around us right now, but they're so elusive we can't detect them directly. As the universe expanded, these neutrinos cooled and slowed, and their tiny mass, we've only recently confirmed they have mass at all, affects the expansion in subtle ways. They're like a cosmic background even older than the microwave background, carrying information from when the universe was denser than an atomic nucleus. Stefan Boltzmann's law tells us how radiation energy density changes with expansion. It falls as the fourth power of the scale factor. Matter density falls as the third power. But dark energy stays constant or nearly so. This is why we live in a special time. For the first few billion years, radiation dominated. Then matter took over. And just recently, cosmologically speaking, about 5 billion years ago, dark energy began to dominate. We happen to live in the transition period when we can still see evidence of all three epochs. The Sunyaev-Zeldovich effect. When cosmic microwave background photons pass through hot gas in galaxy clusters, they get kicked to higher energies by the electrons. This leaves a shadow in the microwave background, but it's a shadow that doesn't fade with distance. Unlike galaxies, which get dimmer as they recede, this effect remains constant. It's like having standard rulers that don't shrink with distance in an expanding universe. Pavel Sunyaev and Yakov Zeldovich, they gave us this tool in the 1970s, but only now are we really exploiting its power. DAISY, the dark energy spectroscopic instrument, is currently mapping millions of galaxies, quasars, and stars to create the largest three-dimensional map of the universe ever made. Each spectrum tells us not just what the object is made of, but how fast it's receding, how the expansion has affected it. It's like taking the pulse of the universe at different times in its history, building up a picture of how the expansion rate has changed. You know, I often think about the information paradox in an expanding universe. Every cubic meter of space contains a finite amount of information. This follows from the holographic principle, from black hole thermodynamics. But if space is expanding, creating new volume, where does the information come from to fill this new space? Is it created from nothing? Is it copied from somewhere? Or is the information density diluting like matter density? The turnover scale in the matter-power spectrum, this marks the transition from radiation domination to matter domination in the early universe. Fluctuations that entered the horizon during radiation domination were suppressed, while those entering during matter domination could grow. This scale, imprinted in the distribution of galaxies, expands with the universe, another cosmic ruler for measuring expansion. Gravitational waves from merging black holes detected by LIGO and Virgo. These ripples in spacetime are affected by expansion too. As they travel across billions of light years, they're stretched just like light waves. But unlike light, we can sometimes see the source in other ways. Optical flashes from merging neutron stars, for instance. These standard sirens, as Bernard Schutz called them, give us a completely independent way to measure the expansion, free from the systematic uncertainties that plague other methods. The trans-Planckian problem troubles me. During inflation, quantum fluctuations are stretched from subatomic to cosmic scales. But if inflation lasted long enough, some of these fluctuations started out smaller than the Planck length, where our physics breaks down. How can we trust our predictions when they depend on physics at scales we don't understand? It's like building a castle on foundations we can't see. Cosmic variance is a fundamental limit to our knowledge. We have only one universe to observe, one realization of the cosmic dice throw, the largest scale fluctuations. We can never know if they're typical or unusual, because we have no other universes to compare them to. It's a kind of cosmic loneliness, being limited to a single example of something so vast. The Alcock-Paczynski test uses the fact that we know galaxy clusters should be roughly spherical on average, not preferentially stretched in any direction. But if we use the wrong expansion model, we'll see them as ellipsoidal, stretched along or perpendicular to the line of sight. It's like looking at reflections in a funhouse mirror and trying to deduce the mirror's shape from how it distorts familiar objects. The lithium problem. Big Bang nucleosynthesis, happening in the first minutes as the universe expanded and cooled, should have produced specific amounts of hydrogen, helium, and lithium. We see exactly the predicted amounts of hydrogen and helium, but only about a third of the expected lithium. Where did it go? Did something in the early expansion destroy it? Or is our understanding of those first minutes somehow incomplete? Quintessence models, scalar fields that could drive acceleration. They remind me of the electromagnetic field, but instead of carrying electric and magnetic forces, they carry the force of cosmic repulsion. Some models have the field slowly rolling down a potential, like a ball rolling down a very gentle slope. Others have tracker solutions where the field naturally evolves to give acceleration regardless of initial conditions. The variety of possibilities is both exciting and frustrating. The Great Attractor, a gravitational anomaly pulling galaxies in our local region, even this massive concentration of matter can only slow the expansion locally, not reverse it. It's like a whirlpool in a river. The water might swirl, might move backward locally, but the river as a whole still flows toward the sea. William Fowler's work on stellar nucleosynthesis showed us that most elements were forged in stars, not in the Big Bang. But the expansion determines how many generations of stars we can have. As the universe dilutes, star formation will eventually cease. The last stars will form perhaps 100 trillion years from now. After that, darkness, with the expansion continuing into an empty future. When I was young, I used to imagine riding on a beam of light. Now I find myself imagining riding along with the expansion of space itself. What would we see? What would we experience? The curious thing is, we are riding the expansion, all of us, right now. Every atom in your body, every cell is embedded in expanding space. We don't feel it because the electromagnetic forces holding us together are so much stronger, but we are surfers on the cosmic wave. Modified Newtonian dynamics, MOND, proposed by Mordecai Milgram, it suggests that perhaps we don't need dark matter at all. Perhaps gravity itself behaves differently at very low accelerations at the edges of galaxies. In Monde, the expansion affects how gravity works on cosmic scales. It's a radical idea and it works surprisingly well for galaxy rotation curves. But it struggles with other observations like the bullet cluster, where we can see dark matter separated from ordinary matter. Still, it makes one wonder, are we missing something fundamental about gravity and expansion? The sound horizon at recombination. This is the maximum distance sound waves could travel in the hot plasma of the early universe before atoms formed. About 450,000 light years at the time, but expanded now to about 490 million light years. This scale is imprinted everywhere in the cosmos, in the cosmic microwave background, in the distribution of galaxies. It's like the universe has a characteristic note, a fundamental tone set by the interplay of gravity and pressure in that ancient plasma. Harrison-Zeldovich spectrum, Edward Harrison and Yakov Zeldovich independently proposed that the initial fluctuations from inflation should have the same amplitude on all scales. Not exactly the same. There's a slight tilt, what we call the spectral index, which tells us about the physics of inflation. The Planck satellite measured this tilt precisely, 0.965, just slightly less than the perfect scale invariance of 1. This tiny deviation, it's a window into the first fraction of a second of cosmic history. Dark energy could be dynamic, changing with time, if it's phantom energy with an equation of state parameter less than 1, the expansion accelerates ever faster until even atomic nuclei are torn apart in a big rip. Robert Caldwell at Dartmouth calculated that if dark energy is phantom, the universe could end in just 22 billion years. Atoms would be destroyed in the final minutes, nuclei in the final fraction of a second. It's a violent end to the gentle expansion we see today. But there's another possibility. Perhaps dark energy will decay, like a radioactive element with a very long half-life. Paul Steinhardt and his colleagues have explored models where dark energy eventually transitions to something else, perhaps even becoming attractive rather than repulsive. The expansion could slow, stop, reverse. The universe could recollapse after all, but only after hundreds of billions of years of expansion. The Lyman alpha forest. When we look at distant quasars, their light passes through billions of years of expanding space, through countless clouds of hydrogen gas. Each cloud absorbs light at a specific wavelength, but expansion stretches these absorption lines to different redshifts. The result is a forest of absorption lines that maps the distribution of matter along the line of sight. It's like reading the autobiography of the universe, written in absorbed light. Juan Maldacena ADA-CFT correspondence suggests something profound about space itself. A gravitational theory in a space with one dimension can be exactly equivalent to a quantum field theory without gravity in one less dimension. What does this mean for our expanding universe? Could the three-dimensional space we experience be a kind of hologram of physics happening on a distant two-dimensional surface? And if so, what does expansion mean in this picture? Peculiar velocities. These are the local motions of galaxies on top of the overall expansion. Our Milky Way is moving at about 600 kilometers per second relative to the cosmic microwave background, pulled by the gravity of nearby structures. These velocities are like eddies and currents in the cosmic flow. They complicate our measurements of expansion, but also tell us about the distribution of matter, including dark matter we can't see directly. The nonlinear regime of structure formation. Once density fluctuations grow large enough, simple linear theory breaks down. Galaxies form, merge, interact in complex ways that we can only understand through massive computer simulations. The Illustrious simulation, the Eagle simulation, the Millennium simulation, these calculate the paths of billions of particles over billions of years, showing how expansion and gravity together weave the cosmic web. The topology of the universe is another mystery. We know space is approximately flat, but flat doesn't mean simple. It could be like a torus, where traveling far enough in one direction brings you back to where you started. It could have more exotic topologies. Jean-Pierre Luminet and his colleagues have searched for patterns in the cosmic microwave background that would reveal such topology, circles in the sky where we see the same regions from different directions. So far, nothing conclusive. The universe might be simply connected, or its topology might be on scales larger than we can observe. Baryogenesis. Why is there more matter than antimatter? This happened in the very early universe, when expansion was rapid and temperatures were extreme. Andrei Sakharov laid out the conditions needed: violation of baryon number, C and CP violation, departure from thermal equilibrium. The expansion itself provides the departure from equilibrium. Without expansion, the universe might have remained perfectly balanced, matter and antimatter annihilating completely, leaving nothing but light. The reheating after inflation. This is when the energy driving inflation was converted into the particles and radiation of the hot Big Bang. It must have been an incredibly violent process, temperatures rising to perhaps 10^16 Kelvin. The details of reheating affect everything that came after: the abundance of dark matter, the spectrum of gravitational waves, perhaps even the origin of matter itself. Yet we understand it poorly, this crucial transition from inflationary expansion to the more sedate expansion we see today. Void galaxies, those rare galaxies that formed in the emptiest regions of space, they're like natural laboratories for studying expansion without the complications of a dense environment. They tend to be bluer, more actively forming stars, less evolved than galaxies in denser regions. It's as if they're younger, having experienced less of the universe's history despite being the same age. The A effect in gravitational lensing. When light from a distant galaxy is bent by the gravity of a closer galaxy, the expansion of space between them affects the lensing. It's a subtle effect, but it gives us another probe of the expansion history. Each lensed image is like a snapshot of the expansion at different cosmic times. The cosmic coincidence problem keeps me pondering late into the night. Why do we happen to live at the precise moment when dark energy and matter density are comparable? For most of cosmic history, one or the other dominated completely. It's like walking into a room just as someone is flipping a coin and seeing it balanced on its edge. Either we're incredibly lucky or there's something deeper we don't understand about the connection between matter and dark energy. Lee Smolin's cosmological natural selection. Now, there's a wild idea. He suggests that black holes might give birth to new universes, each with slightly different physical constants. Universes that produce many black holes have many descendants. And what kind of universe produces lots of black holes? One with stars, galaxies, complexity, perhaps one with expansion rates and dark energy values like ours. Evolution, but on a cosmic scale. The expansion itself might be selected for, in a sense. The running of the spectral index, the tilt in the primordial fluctuation spectrum isn't quite constant. It has a very slight scale dependence, what we call running. The Planck satellite constrains this to be less than 0.01, but even this tiny number tells us about the inflaton potential, the field that drove inflation. It's remarkable. From observations today, we can constrain physics at energies a trillion times higher than the Large Hadron Collider can reach. Silk damping in the early universe. Before recombination, photons and baryons were tightly coupled, but not perfectly. Photons could diffuse slightly, washing out small-scale fluctuations like hot water dissolving sugar cubes but leaving larger lumps intact. This process, named after Joseph Silk, set the minimum scale for the first structures. Without it, the universe might have formed tiny black holes instead of stars. The redshift desert between Z equals 2 and 3. For some reason, we see fewer quasars and galaxies at these redshifts. Is it a real feature of cosmic history, a time when star formation paused, or is it observational bias, these objects being particularly hard to detect? The expansion history during this epoch is crucial for understanding galaxy evolution, but it remains murky, like trying to read through frosted glass. Tomographic surveys slice the universe into shells of different redshift, different look-back times. Each shell shows us the universe at a different age, affected differently by expansion. It's like having a time machine, but one that only lets us look, not touch. The Dark Energy Survey, using the Blanco telescope in Chile, has photographed hundreds of millions of galaxies this way, building a three-dimensional map of the expanding cosmos. The back reaction problem? Can the lumpy, inhomogeneous universe we see average out to the smooth, homogeneous expansion of our models? Thomas Buchert and others have shown that in principle the formation of structure could affect the average expansion rate. It's like asking whether the weight from many boats could change the flow of the river itself. Most cosmologists think the effect is small, but some argue it could explain acceleration without dark energy. Chameleon fields. These are theoretical dark energy fields that change their properties depending on the local environment. In dense regions like Earth, they're hidden, chameleonic, having little effect. But in the sparse voids of space, they could drive acceleration. Experiments like the Eötvös torsion balance at the University of Washington are searching for such fields, looking for fifth forces that could be dark energy in disguise. KBC void. We might be living inside an enormous cosmic void, a billion light years across. If true, this could affect our measurements of expansion. Light from distant supernovae would be affected by the void's gravitational field, potentially explaining some of the Hubble tension. It's unsettling to think that our location might be special, that we're not typical observers in a typical region of space. Pre-Big Bang cosmology Gabriele Veneziano and Maurizio Gasparini have explored what might have come before our expanding phase. In string theory, there could have been a previous phase of contraction and increasing curvature, which bounced into our current expansion. The transition would leave signatures, gravitational waves with specific patterns, perhaps anomalies in the cosmic microwave background. We're searching for these whispers from before the beginning. The phantom divide at W equals 1. This marks the boundary between dark energy that could be a cosmological constant and phantom energy that would lead to a big rip. Current measurements place us tantalizingly close to this divide. The Euclid Space Telescope, launched in 2023, is designed specifically to measure which side we're on. Its surveys will map billions of galaxies, looking for the subtle effects of dark energy on structure formation. Primordial black holes. If they form from the largest fluctuations in the early universe, they could be the dark matter. The expansion rate during their formation determines their mass. Form too early, and they evaporate through Hawking radiation. Too late, and they're too massive to be dark matter. It's a delicate balance set by the interplay of quantum fluctuations and cosmic expansion in the first second after the Big Bang. The polarization of the cosmic microwave background. This tells us about the universe when it was 380,000 years old, but also about later times, when this ancient light was scattered by electrons in galaxy clusters or during reionization. The E modes and B modes, different patterns of polarization, carry different information. B modes in particular could reveal primordial gravitational waves from inflation, the smoking gun of that early accelerated expansion. Martin Rees's observation that we live in a special epoch, not just the coincidence of matter and dark energy densities, but also that we can see the cosmic microwave background, that galaxies are neither too close nor too far, that the night sky is dark but not empty. A few billion years earlier, the universe was opaque to observations. 100 billion years from now, evidence of the Big Bang will be nearly gone. We exist at the perfect time to understand our cosmic origins. Let me tell you about cosmic shear, the weak gravitational lensing of distant galaxies by all the matter along the line of sight. Every galaxy we see is slightly distorted, stretched tangentially around mass concentrations. By measuring millions of these tiny distortions, surveys like KIDS and DES map the dark matter and measure how structure grows as the universe expands. It's like reading the universe's palmistry, deducing its nature from the patterns we see. The Sachs-Wolf effect, different from the integrated version I mentioned, this is the gravitational redshift of photons climbing out of potential wells at the time of last scattering. Denser regions appear cooler in the cosmic microwave background, less dense regions warmer. These temperature variations, just parts in 100,000, are the seeds from which all structure grew. Without them, the universe would have remained perfectly smooth, expanding into eternal emptiness. There's a quietness to contemplating the expansion, isn't there? A kind of cosmic humility that comes from realizing that the universe is not just larger than we imagined, but growing larger every moment. And in this growth, in this ceaseless stretching of space itself, we find clues to the deepest mysteries of existence. Robert Kirshner at Harvard, one of the leaders of the High Z supernova search team that discovered acceleration, he likes to say that dark energy is not just the most abundant stuff in the universe, but also the most embarrassing. Here we are in the 21st century with our particle accelerators and space telescopes, and we're forced to admit that we don't know what 70% of the universe is made of. It's wonderfully humbling, really. The integrated Sachs-Wolf effect I touched upon, let me delve deeper. When the universe was matter-dominated, gravitational potentials were constant. But once dark energy began to dominate, these potentials started to decay. A photon falling into a cluster finds a shallower potential when it climbs out. It gains energy, appears hotter. We can see this as a correlation between the cosmic microwave background temperature and the positions of galaxy clusters. It's it's like watching the universe change its mind about gravity in real time. Reionization. This was the universe's second major phase transition, about a billion years after the Big Bang. The first stars and galaxies lit up, their ultraviolet light ionizing the neutral hydrogen that filled space. The expansion played a crucial role. It had to slow enough for structures to form, but not so slow that everything collapsed before stars could ignite. The timing was exquisite, like a cosmic choreography between gravity and expansion, the Gunn-Peterson trough in quasar spectra. James Gunn and Bruce Peterson predicted in 1965 that if we looked far enough back, we'd see where the universe was still neutral before ionization. The Sloan Digital Sky Survey finally found these troughs in 2001 in quasars at redshift 6 and beyond. The expansion has carried these quasars so far that we're seeing them as they were when the universe was less than a billion years old. Nick Kaiser's rocket effect. Peculiar velocities of galaxies affect their observed redshifts, creating what looks like elongation along the line of sight in galaxy surveys. On large scales, where galaxies are falling together, this creates apparent compression. The interplay between real expansion and these velocity-induced distortions tells us about both the expansion rate and the growth of structure. It's like listening to an orchestra and trying to separate the individual instruments. The turnover in the matter-power spectrum, I mentioned this before, but let me elaborate. It marks the horizon size when the universe transitioned from radiation to matter domination, about 50,000 years after the Big Bang. Fluctuations larger than this scale grew normally, smaller ones were suppressed. This characteristic scale, now expanded to about 100 megaparsecs, is imprinted in the distribution of galaxies like a fossil from when the universe changed gears. Cosmic crystallography, the search for repeating patterns that would indicate a finite, multiply-connected universe. Jean-Pierre Luminet calls it looking for the ghosts of cosmic topology. If the universe is finite but unbounded, like the surface of a torus, we might see the same galaxy cluster from different directions, at different distances, at different ages, due to light travel time. The expansion makes this search incredibly complex. The ghosts would appear at different redshifts, different sizes. The missing baryon problem? Big Bang nucleosynthesis tells us how many protons and neutrons there should be. But when we count up all the stars, gas, and dust we can see, we only find about half. Where are the rest? Recent observations suggest they're in the warm, hot, intergalactic medium, gas at millions of degrees filling the filaments of the cosmic web. The expansion has spread this gas so thin it's nearly impossible to detect, like trying to see steam in a vast, dark room. Gravitational redshift versus cosmological redshift. They're fundamentally different phenomena, though both shift light to longer wavelengths. Gravitational redshift comes from climbing out of gravity wells, cosmological redshift from the expansion of space. But in an expanding universe with structure, we see both effects combined. Light from a distant galaxy is both cosmologically redshifted by expansion and gravitationally shifted by all the matter it passes. Disentangling them is like trying to separate sugar from coffee after stirring. The fate of information in an expanding universe troubles me deeply. If the universe expands forever, if regions become causally disconnected, what happens to quantum entanglement between particles that end up in different regions? Does the expansion break the entanglement? Or does it persist, creating correlations between regions that can never communicate again? It's a puzzle at the intersection of quantum mechanics and cosmology. Stochastic gravitational wave backgrounds from the early universe. Unlike the gravitational waves LIGO detects from merging black holes, these would be a cosmic hum, gravitational waves from all directions. Different sources, inflation, cosmic strings, phase transitions, would create different spectra. The expansion affects these waves just like light, stretching their wavelengths. Pulsar timing arrays like nanograv are searching for these whispers from the infant universe. The Copernican principle, the assumption that we're not in a special place in the universe, it's fundamental to cosmology. But what if we're wrong? What if acceleration isn't universal, but local? David Wiltshire's timescape cosmology suggests that the apparent acceleration might be an effect of inhomogeneity, that time runs at different rates in voids versus clusters. It's radical, probably wrong, but it reminds us to question our assumptions. The Lillo effect in redshift space distortions. On the largest scales, all galaxies at a given distance should show the same redshift, but their peculiar velocities add noise to this signal. However, this noise itself carries information. The statistics of these velocity-induced distortions tell us about the growth rate of structure, which depends on both the expansion history and the nature of gravity. Every galaxy's redshift is like a vote in a cosmic election, and we're trying to determine the outcome from a partial count. The sound speed of dark energy. If dark energy is a field rather than a constant, disturbances in that field propagate at some speed. For quintessence, this is the speed of light. But for more exotic models, it could be different, even faster than light, without violating relativity. The sound speed affects how dark energy clusters or fails to cluster, leaving subtle signatures in the cosmic microwave background and large-scale structure. Type Ia supernovae are standard candles. We assume they're standard, but are they really? Different progenitor systems, different metallicities, different ages might produce slightly different peak luminosities. Peter Hoflich and others have shown that these differences are small, but in an expanding universe where we're looking across billions of years of cosmic evolution, small systematic errors can masquerade as new physics. The WOW parameterization of dark energy evolution. Beta zero is the equation of state parameter today. WOW describes how it changes with expansion. It's a simple model, probably too simple, but it lets us search for evolution in dark energy without assuming a specific theoretical model. Current constraints suggest WA is close to zero. Dark energy isn't changing much, but the uncertainties are still large. We're like archaeologists trying to reconstruct a civilization from a few pottery shards. When Max Tegmark speaks of the mathematical universe hypothesis, suggesting that our physical reality is a mathematical structure, I find myself wondering what this means for expansion. Is the expansion of space just the unfolding of mathematical relationships? Are we witnessing geometry itself, evolving according to some deeper principle we haven't yet grasped? The equations of general relativity describe expansion, but perhaps they are not just descriptions. Perhaps they are the reality itself. Void galaxies tell us stories of isolation. NGC 7077, sitting alone in a vast emptiness. It formed and evolved with minimal interaction, minimal merging. These galaxies are like controlled experiments in galaxy formation, showing us what happens when expansion dominates over gravitational interaction from the very beginning. They tend to be smaller, bluer, still forming stars while their cluster cousins have long gone quiet. The radio silence of the cosmos. SETI has been listening for decades, and we hear nothing but natural phenomena. Could expansion be part of the answer to Fermi's paradox? Advanced civilizations might arise, but the accelerating expansion ensures they remain forever isolated, each in their own observable universe. By the time a civilization becomes capable of intergalactic communication, the universe has expanded so much that other galaxies are unreachable. We might not be alone, but expansion ensures we're effectively alone. Adam Rees's latest measurements using Cepheids and Type Ia supernovae, they consistently find a higher expansion rate than what we infer from the cosmic microwave background. This tension has only grown stronger with better data. It's at 5 sigma now, the gold standard for discovery in physics. Either we're missing something systematic in our measurements, or the universe is telling us something profound about dark energy, about new physics beyond our standard model. Let me share something that amazes me. The cosmic web looks remarkably similar to neural networks, to the internet, to mycological networks in forests. Is this similarity coincidental, or does it hint at some deeper principle? Growth, connection, and expansion seem to create similar patterns across vastly different scales. Perhaps there's a universal mathematics of networks that applies whether the nodes are galaxies, neurons, or computers. The bootstrap paradox in eternal inflation. If inflation is eternal, producing infinite pocket universes, then everything that can happen does happen, somewhere. Every possible arrangement of particles, every possible history exists in some pocket universe. But then what does it mean to explain anything? If everything happens, have we explained nothing? It's like having a theory that predicts all possible outcomes. Is that really a theory at all? Weinberg's prediction of the cosmological constant. Before dark energy was discovered, Steven Weinberg used anthropic reasoning to predict its value. If it were much larger, the universe would expand too fast for galaxies to form. If it were negative and too large in magnitude, the universe would collapse before life could evolve. He predicted it should be just about what we measure. Was this brilliance or luck? It troubles me that we might need to invoke our own existence to explain fundamental constants. The clustering of dark energy, or rather, its lack of clustering. Unlike matter, which clumps under gravity, dark energy seems perfectly smooth. The ISW effect, the absence of fluctuations in dark energy density, they all point to something that fills space uniformly. But why? What principle demands this smoothness? It's as if dark energy refuses to participate in the gravitational dance that shapes everything else. Helium reionization happened earlier than hydrogen reionization, when the universe was just 100 million years old. The first massive stars, perhaps hundreds of times the mass of our sun, produced intense ultraviolet radiation that could doubly ionize helium. These stars lived fast, died young in brilliant supernovae. The expansion rate during this era determined how quickly these stellar monsters could form, how much they could influence their surroundings before space diluted their effects. The great observatories, Hubble, Spitzer, Chandra, now Webb, each has revealed different aspects of expansion. Hubble showed us acceleration directly through supernovae. Spitzer, seeing in infrared, pierced through dust to show us galaxies in the early universe when expansion was decelerating. Chandra's X-ray vision reveals hot gas in clusters, tracing how expansion and gravity compete. Webb now shows us the first galaxies, when the universe was just beginning to slow its initial rapid expansion. I sometimes wonder about consciousness and expansion. If consciousness emerges from information processing, and if information is limited by the holographic bound, then the expanding universe is constantly creating room for new consciousness, new thoughts, new experiences. Every cubic meter of new space is potential for billions of bits of information. The universe isn't just getting bigger, it's increasing its capacity for complexity, for thought, for experience. Baryon acoustic oscillations at different redshifts. The BAO scale gives us what Eisenstein calls a standard ruler. But we see this ruler at different times in cosmic history when the expansion rate was different. by measuring how the apparent size of this ruler changes with redshift. We trace the expansion history. It's like having photographs of the same person at different ages, reconstructing their growth from child to adult. The sound horizon at matter radiation equality. This is different from the sound horizon at recombination. It marks when the universe transitioned from radiation dominated to matter dominated about 50,000 years after the Big Bang. This scale, about 130 megaparsecs today, shows up in the correlation function of galaxies as a subtle feature. It's amazing that we can see the imprint of events from when the universe was younger than Homo sapiens as a species. Richard Gott's Copernican argument about our future: if we're random observers in time, we're likely to be somewhere in the middle of humanity's existence, not at the beginning or end. Combined with the accelerating expansion, this suggests a finite future for intelligence in the universe. But perhaps intelligence will transcend biology. Perhaps it will find ways to survive even in an exponentially expanding, cooling universe. The expansion sets challenges, but challenges have always spurred innovation. Neutrino masses affect expansion in subtle ways. These ghostly particles were relativistic in the early universe, acting like radiation. As expansion cooled them, they became non-relativistic, acting like matter. But their tiny mass means they can still stream freely, suppressing structure formation on small scales. The expansion history is written in the clustering of galaxies, and neutrinos edited that text in small but measurable ways. The dipole in the cosmic microwave background, our motion through space. We're moving at 370 kilometers per second toward the constellation Leo. This motion is our local response to the gravitational pull of nearby structures, the Great Attractor, the Shapley supercluster. But these structures themselves are participating in larger flows, perhaps streams and currents in the cosmic expansion that we're only beginning to map. You know what I find particularly beautiful? The universe had to expand at just the right rate for us to exist, too fast, and matter would never have clumped into stars and galaxies. Too slow, and everything would have collapsed into black holes long ago. The expansion rate is like a cosmic thermostat, set precisely to allow complexity to emerge and evolve. Whether this is coincidence, necessity, or selection, we don't know. The silence between the galaxies grows wider every second, every heartbeat. The universe becomes a lonelier place. And yet, in this loneliness, in this vast, expanding darkness, we find something profound. We find that we are the universe's way of knowing itself, of comprehending its own expansion, its own destiny. Freeman Dyson once speculated about the far future, about what intelligence might do in an ever-expanding, ever-cooling universe. He imagined beings slowing down their thoughts, hibernating for eons, waking briefly to think and observe before sleeping again. As the universe cools, less energy is needed for computation. Perhaps consciousness could persist indefinitely, experiencing infinite subjective time despite the universe's finite energy resources. The expansion doesn't necessarily mean the end of thought, just its transformation. The crossover from deceleration to acceleration happened when the universe was about 7 billion years old, roughly half its current age. If we could have been there, would we have noticed anything? No. The transition was gradual, imperceptible on human timescales. It's only by looking across billions of years that we see the change. We live our brief lives in what seems like a static cosmos, but we're actually witnessing one frame of a vast, slow-motion movie. Loop quantum cosmology suggests that the Big Bang might not have been the beginning, but a bounce from a previous contracting universe. The expansion we see might be just one phase in an eternal cycle, though not the simple cyclic model I mentioned earlier. In this view, when we trace expansion backward, We don't reach a singularity, but a moment of maximum density before a prior contraction phase. The universe has no beginning, no end, just eternal transformation. The Unruh effect predicts that an accelerating observer sees thermal radiation, where an inertial observer sees vacuum. In an expanding universe, this raises profound questions. Are we embedded in expanding space, seeing particles that wouldn't exist in a static universe? Is some of what we call dark matter or dark energy actually a consequence of our accelerated reference frame? These questions push at the boundaries between general relativity and quantum mechanics. When I think about the meaning of expansion for humanity's future, we are living in a brief window when the universe is knowable. The evidence for the Big Bang, the cosmic microwave background, the primordial light elements, all of this will eventually disappear. In 1 trillion years, beings in our galaxy won't be able to discover the expansion. They'll see a static island universe, much as astronomers before Hubble did. We are privileged to live when the universe's history is still readable. String theory suggests extra dimensions beyond the three of space and one of time that we experience. How do these extra dimensions behave as our familiar dimensions expand? Are they static, expanding too, contracting? The way these hidden dimensions evolve could determine the properties of particles and forces we observe. The expansion of our universe might be just one aspect of a higher dimensional evolution we can only glimpse indirectly. Penrose's conformal cyclic cosmology, which I touched upon, it relies on a profound mathematical insight. In the far future, when all matter has decayed and only photons remain, the universe becomes conformally flat. The mathematical description of this infinite future is identical to that of the Big Bang of a new eon. It's as if the universe forgets its scale and infinite expansion becomes indistinguishable from a point-like beginning. The anthropic principle keeps returning to my thoughts. The expansion rate, the dark energy density, the initial fluctuations, they all seem fine-tuned for complexity, for life, for consciousness. Is this evidence for a multiverse where we naturally find ourselves in a rare, hospitable universe? Or does it point to something deeper, some principle we haven't discovered that requires these values? The expansion itself might be necessary for observers to exist to observe it. Gravitational entropy, as Penrose describes it, the early universe had incredibly low gravitational entropy, with matter spread smoothly rather than clumped into black holes. This set the arrow of time, allowing the universe to evolve from simple to complex. The expansion plays a crucial role, preventing immediate gravitational collapse, giving time for stars, planets, and life to form. Without expansion, the universe would have reached maximum entropy, all black holes, almost immediately. The galaxy NGC 1277 contains a black hole weighing 17 billion solar masses, a significant fraction of the galaxy's total mass. Such monsters formed early in cosmic history when the universe was denser. As expansion dilutes matter, forming such massive black holes becomes impossible. We're seeing fossils from an era when the universe was young and violent, when expansion hadn't yet gentled the cosmic environment. The lithium problem I mentioned, it might be telling us something about expansion during the first minutes. Perhaps there were slight departures from the standard expansion rate or inhomogeneities we haven't accounted for. Every discrepancy between theory and observation is an opportunity, a crack through which new understanding might enter. Quantum discord, a type of quantum correlation beyond entanglement. How does it behave in an expanding universe? As space expands, does quantum discord between separated particles decrease, or does it persist, creating a kind of cosmic quantum memory? These are questions at the frontier, where quantum information theory meets cosmology. The great cold spot in the cosmic microwave background, spanning hundreds of millions of light years, Is it a super void, a vast emptiness in the cosmic web? Or is it something more exotic, evidence of another universe bumping into ours during inflation, a texture in space time, or something we haven't imagined? The expansion has carried this feature across billions of light years, preserving it like a cosmic fossil for us to puzzle over. As I contemplate all of this, the vast scales, the deep time, the inexorable expansion carrying everything apart, I'm struck not by despair but by wonder that we, collections of atoms forged in stars, can comprehend the expansion of the universe itself. This is perhaps the most remarkable thing of all. We are the universe becoming conscious of itself, understanding its own growth, its own evolution, its own possible futures. The expansion of space, it's not just a physical phenomenon, it's a meditation on time, on change, on the nature of existence itself. Every night when you look up at the stars, you're seeing the expansion in action. The light from those stars has been stretched by the growing space it traveled through. You're seeing the universe's autobiography, written in red-shifted light. And so, as you drift off to sleep tonight, remember that you're part of this grand expansion. The atoms in your body have been on a 13.8 billion year journey through expanding space. You are not separate from the cosmos, but an integral part of its unfolding story. The same forces that drive galaxies apart have shaped the particles that make you who you are. The universe expands, time flows forward, entropy increases. And yet, against this backdrop of cosmic evolution, complexity emerges, consciousness awakens, understanding grows. We are local decreases in entropy, temporary patterns of order in an expanding, evolving cosmos. And in our brief moment, we've discovered the expansion itself, this fundamental truth about our universe. Perhaps that's enough for tonight. The universe will continue its expansion as you sleep. Galaxies will drift imperceptibly further apart. Space itself will grow. But for now, rest. Let these cosmic thoughts settle like stardust in your mind. If you've enjoyed this journey through the expanding universe, please consider subscribing to this channel. We're working toward our first 1,000 subscribers, and your support helps us create more of these peaceful explorations of high-quality knowledge. Click the like button if this has helped you relax, and you'll see more stories like this, more voyages through science, philosophy, and the wonders of existence. Tomorrow night, perhaps we'll explore other mysteries, the nature of time, the puzzle of consciousness, the search for other worlds. But for now, let the expansion of the universe be your lullaby. Good night, sleep well, and may your dreams be filled with the gentle wonder of an ever-growing cosmos.